Greetings, everyone. Welcome back into the world of trigonometry. I'm Professor Simon, and I want to continue our discussion of right triangle trigonometry with some special angles and some important basic identities that are going to come up everywhere you use trigonometry. Okay, so the special angles first. These angles are special because of the symmetries that they cause, or because of the important shapes that they come from, or just because they happen to occur a lot in the nature of the things that we study in physics, chemistry, so on and so on. And they work really well in certain ideas of trigonometry. These are the ones that instead of using a calculator, you're going to be expected to have them memorized. You have to know these by heart for a lot of applications, because instead of accepting decimal answers, a lot of times they will want exact answers. And you'll see what I mean in just a second. Let's start with 45 degrees. 45 degrees doesn't sound like something that you'd hit all the time, but if you think about it for a second, 45 degrees is exactly half of 90. And remember, 90 is crucial for all of the systems that we create in our mathematical world. And that also means that 45 is an evenly sectioned portion of 180 and 360 are measured rotations. 180 being the connection to pi radians, and 360 of course being a full rotation. To convert 45 degrees into radians, it can be exactly converted into pi over 4. Now that should make sense, because remember, pi is the same thing as 180 degrees. And 45 degrees is a quarter of that. So that would make it pi over 4. Later on, whenever you see any of our radians with an over 4, it will always be linked back to our 45 degree angle. Okay, so how is 45 special? Outside of our normal system, just in the normal right triangles, 45 degrees causes the only isosceles right triangle. Because remember, to be in the right triangle, the other two angles besides the right angle have to be complementary. They have to add up to 90 to make the total 180 degree internal triangle sum, angle sum. Well, I know that it's isosceles because these two angles have to be the same. 45 and 45 is 90. These two angles being the same causes these two sides to be the same. To make things as basic as possible, what I'll do is I will choose the simplest number that works with it being isosceles. So I'll choose 1 and 1 for those two sides. You could really pick any number you want, but we want to keep it basic here. So now, if I know those two are equal at 1, I can use Pythagorean Theorem to find the other side there. 1 squared plus 1 squared is 2, and then I have to take the square root. So this side over here is going to be the square root of 2. Now that I have all of the sides set up, I can write down the ratios of the sine, cosine, and tangent of 45 degrees. All right, so sine of 45 degrees would be the opposite over the hypotenuse, which is going to be 1 over square root of 2. Now, of course, in a lot of places, people aren't going to want you to write something that has a radical in a denominator. And that's really going to be up to whoever your professor is and how picky they want to be on things. But also keep in mind that sometimes you need to combine fractions with other things, and having a radical denominator may not be the best anyway. So I'm going to rationalize this by multiplying the top and bottom by the square root of 2. Like so. I will get the alternative form of square root of 2 over 2. And that's going to be the sine of 45 degrees. Cosine of 45 degrees, notice, is going to be the same thing. That should make sense to you because it's an isosceles triangle. The angles are equal, the sides are equal on the legs. So the sine and cosine are going to have the same ratio. And then tangent, opposite over adjacent, is 1 over 1. I just get 1. Okay? Now, of course, as we'll talk in a minute, the other three trigonometric ratios, cosecant, secant, and cotangent, are going to end up just being the reciprocals of these. Okay? So just keep in mind that for any of those, I'm going to take these same ratios and just flip them, do the reciprocal, right? So for example, sine is the reciprocal of cosecant. So the cosecant of 45 would be square root of 2 over 1. So in other words, what I'm saying is you really only need to memorize these three. And from here, you can always create the other three if you need to. Personally, me, I'm terrible at memorizing things. What I've always done is remember the triangle. The fact that 45 degrees is the only angle inside of a right isosceles triangle. And then the rest of it sort of falls apart with all of the sides and everything. All of the trig information's in that diagram. This is just interpreting it. So if it helps you, to remember the diagram like me, do that. Or if you're a person that just likes to know the cold, hard facts on it and just memorize the numbers, then do that too. Okay? Or do that, either. The next two special angles go together because they are complementary. 60 degrees and 30 degrees are complementary. So whenever you create one of them in a right triangle, you're also going to make the other one in a right triangle. The way we create them, though, is I start with an equilateral triangle. An equilateral triangle, all sides are equal, all angles are equal to each other. That means that all of the angles have to be 60 degrees. That's the only way you can do an equilateral triangle. And what I want to do is create a right triangle out of that. So what I'm going to end up doing is cutting this thing exactly down the middle. And since an equilateral triangle is perfectly symmetric, side to side like that, the line that causes a right angle is called an altitude that goes through the other vertex up here. The altitude happens to also be a bisector because of the symmetry of the equilateral triangle. So if this is a bisector, it's also an altitude, which means it causes a right angle. Since I'm cutting this thing in half, I'm going to choose the equilateral triangle to have sides of length 2. All of the sides are equal. If I do that right, it doesn't really matter, but 2 is something I can cut in half easily, because notice, that's what I'm going to do. I'm going to cut this in half. So when I take just this right side over here, 2 is the hypotenuse, and 1 is the leg connected to the 60 degrees. In other words, 1 is adjacent 60 degrees. 1 is also opposite 30 degrees. So whichever way you want to look at that. Okay, it has to be that way because that's how an equilateral triangle would be set up. It gave me 2 of the sides. I can then use Pythagorean Theorem to find the third side. Since this is a hypotenuse, I would be subtracting. 2 squared is 4, minus 1 squared is 1, 4 minus 1 is 3, and then I would have to square root. So I would get the square root of 3 for that other side of the triangle. And just like before, all of the information is now there in that diagram, but I can create the sine, cosine, and tangent of 60 degrees and of 30 degrees. Incidentally, just like before we were talking about the radian measure, 60 degrees is going to be pi over 3, and 30 degrees is going to be pi over 6 in radians. And again, that should make sense to you because pi is the same as 180 degrees, and 180 divided by 3, think of 18 divided by 3 being 6, right? Or 18 dividing by 6 to give you 3. That's the connection there that you can remember. All of the radian angles later on that have a denominator of 3 and they're simplified will be somehow connected to 60, vice versa. Simplified radian angles with a denominator of 6 will be connected to your 30 degree type of setup. All right, so let's go ahead and write these down. The sine of 60 is going to be the opposite over the hypotenuse. That's square root of 3 over 2. Cosine of 60 is 1 over 2. Tangent of 60 is opposite over adjacent, square root of 3 over 1. is the square root of 3. Okay? Now 30 degrees. Be careful you're paying attention to where that angle is. 30 degrees is opposite the 1 side and adjacent to the square root of 3 side. So sine of 30 is opposite over hypotenuse. That's 1/2. Cosine of 30 is the adjacent over the hypotenuse. That's going to be square root of 3 over 2. And tangent of 30 is going to be 1 over square root of 3, opposite over adjacent. And that's going to be one of the ones that you're going to want to remember how to fix. I'll multiply top and bottom by square root of 3. So this will actually be square root of 3 over 3. Okay? So these three angles, 45 degrees, 60 degrees, 30 degrees, you must know these. These are angles that come up in all applications of trigonometry, and they will require that you give exact answers like square root of 3 over 2, not decimal answers that the calculator would give you instead of that if you were to punch up sine of 60 degrees. Okay? So remember, you have to know these particular angles. Most teachers will require this of you. I know I require it of my students. Okay? Now let's talk about some identities. These are basically consequences of the way that we've defined these ratios. And what they give us are ways of interacting all of the different trigonometric ratios with each other in ways that will help us simplify and solve for other things. So in a sense, part of the algebra of reducing and understanding trigonometry comes out of knowing these identities. They're a lot like formulas, but we call them identities because of the way they're always some sort of equality that's always the same setup and balance. Okay? So these allow us to understand a lot of the connections. And even when something doesn't seem like it's simplifiable, these identities make simplifying the trigonometric equations and expressions a lot more simple. Also, later on, these identities become ways that trigonometry will stand out from other branches of math in important ways that would make you want to use it in certain circumstances when other branches might fail. Okay, so let's start with the reciprocal identities. The reciprocal identities basically are straight out of the definitions of the 6 trig ratios. If you remember, sine of A is going to be A, little a, over little c. And then cosecant is little c over little a. It was simply defined that way. That means they're reciprocals of each other. So in other words, 1 over, or 1 divided by sine of A is going to equal the cosecant of A. And also that's vice versa, by the way. 1 over cosecant of A is going to be equal to sine of A. Another way of writing a reciprocal is two things that multiply to equal 1. So the sine of A times the cosecant of A will equal 1. Okay? 1 over cosine of an angle is the secant of an angle, and 1 over tangent of an angle is the cotangent of that angle. This is basically, like I said, part of the setup of it, and it's also the reason why you don't see the cosecant, secant, and cotangent buttons on your calculator, because it's just not necessary. If you have the sine, cosine, and tangent buttons, all you have to do is 1 over reciprocate any one of those, and you can have the other one of the other 3 calculations. So you don't need multiple buttons. To shrink the world of trig a little bit more, let's talk about the quotient identities. The quotient identity basically says that the tangent of any angle is equal to the sine of that angle divided by the cosine of that angle. And again, that comes out of the definition, but not quite as direct. If I take the sine of A, little a over little c, and the cosine of A, that would be little b over little c, because that's adjacent of A over hypotenuse, and divide them. So A over c divided by b over c. In order to divide a fraction, I have to flip it and multiply, right? Do the reciprocal and multiply. Notice the c's will reduce, and I'm left with A over b, which is tangent of A, the opposite over the adjacent. So as you can see, it is from the definition, and it's basically just a fraction simplification. Again, what this tells you is you need even one less button on your calculator. Tangent's there just as a convenience, really. But if you can get the sine and the cosine of an angle, you can build the tangent. Think about that for a second. If I can build tangent from sine and cosine, and I can build the other three from sine, cosine, and tangent, then really, am I not building all six just from sine and cosine? Which is true, okay? In fact, any two of them, you can find a way to mix and match these two sets of identities together. And if you know any two of the trig ratios, well, not any two. If you know tangent and cotangent, that's not going to work out very well because those are directly linked. But if you know two different sets, then you can use these to figure out the rest of them. Okay. Incidentally, cotangent of A is cosine of A over sine of A. That should be obvious because tangent and cotangent are reciprocals. So of course they would, just be the flip, the reciprocal of each other here. Okay, now the biggest identity that's used the most in all of trigonometry and things that lean on trigonometry are the Pythagorean identities. And these are called that because they come out of the Pythagorean Theorem, which of course is important here because we've defined all of our trig ratios off of right triangles, right? So the legs squared sum, a squared plus b squared, has to equal the hypotenuse squared, right? That's our Pythagorean identity because this is a right triangle. If you divide by c squared, like so, notice this side will be 1, and then I can basically rewrite the squares just on the whole fractions, a over c squared and b over c quantity squared, like this. But remember, a over c is the sine of a, and b over c is the cosine of a. And then that's squared. In trigonometry, we use a shorthand for writing exponents. Okay? Here, let me give you a generic structure. Anytime you have a trig of some angle, right, that's sine, cosine, tangent, secant, cosecant, cotangent, and it's raised to some power n, this is always going to be shorthand written where the exponent appears between the trig function and the angle. This is just a shorthand, okay? It does not mean that I'm doing the sine twice. It means you're finding the sine value of this angle, because that's the only thing that makes sense. You have to have a sine of an angle. And then you're squaring that ratio afterwards, okay? This is just a shorthand that they use instead of having to write parentheses all over the place and getting lost in those and getting confused, okay? Incidentally, you can divide by a squared or you can divide by b squared up here and get a different Pythagorean identity. You have tangent squared of an angle plus 1 is equal to the secant squared of the angle, or 1 plus cotangent squared of the angle is equal to cosecant squared of that same angle. Okay? These three identities right here give not very obvious connections. Sine and cosine, it kind of makes sense for them to be connected, because you kind of feel that with the words and everything. But tangent related to secant, cotangent related to cosecant, those don't always come like right out of looking at the diagram there. Okay? With these identities, you actually only need to know one trig ratio. If I know one trig ratio, then I can use one of these three identities to get from that value to another one. And then once I know those two, I can use these two groupings to fill out the rest. So in actuality, if you know just enough about an angle to get one trig ratio, doesn't matter which of the six, I can build from the other ones all of the rest of the trig ratios. And you can also do that from a diagram too, by the way. If you know enough about an angle to know one ratio, then that means you know two of the sides. And you can use Pythagorean Theorem to fill out the third side and then get all the information from it. Okay, so there's two ways to approach that particular type of problem. Let's get an example real quick of this. Look, let's pick any angle that would fit in a right triangle. Let's say 57 degrees, right? Okay, sure, 57 degrees. So in my calculator here, I'm going to punch up the sine of 57 degrees, and I'm going to square it. Right? Sine 57 degrees squared plus the cosine of 57 degrees squared. And I want you to notice that the calculator gave me 1. It doesn't matter what angle you pick. Okay? Here, just in case you missed the other part of it, I put plus cosine 57 squared there. And when I hit enter, of course, we got 1. And you could do that with any of these. Okay? You can do the tangent of 57, then square that quantity plus 1, and you'll get 1 over the cosine, whatever that is, that thing's squared, right? Because secant's 1 over cosine. You'll notice I didn't have to write any fractions here. Back in one of the other lectures, remember me calling secant, cotangent, cosecant the functions of convenience. And this is the convenience right here. I didn't have to write any of these formulas, any of these identities in fraction form, right? So that they're doing their job right there. They're making it very convenient for me to see the pattern that's going on. All right, one more pattern that I want to point out here is the complementary angles pattern, the cofunction pattern. So in a right triangle, remember we've already said this earlier and we said it in another one, the two other angles have to be complementary, because the 3 angles in the triangle have to add up to 180 degrees, and we've already accounted for 90 of those degrees because it's a right triangle. So then the measures of A and B have to add up to be 90 degrees, no matter which angle you pick to fit in the right triangle. Okay, so then what that means is I could set up one of the angles, I used B, doesn't matter, to be 90 degrees minus the other angle, minus A. And typically what we call that is the complement of A. Whenever you see 90 degrees minus an angle, or by the way, if it's in radians, you could also see it as pi over 2 minus an angle. Anytime you see that kind of setup, don't just read it literally, pi over 2 minus A, 90 degrees minus A. Think of it as the complement of angle A. That's what that's saying. So B is the complement of angle A, is the way you can read that. All right, well, again, from the triangle, notice sine of angle A is A over C. Cosine of angle B is A over C, the same thing. They're equal. You think back one scene, notice that the sine of 60 and the cosine of 30 are equal, and the sine of 30 and the cosine of 60 are equal because they're complementary, not just a coincidence. It's because they're all coming from that same triangle, just on opposite ends. Pun intended, opposite end, right? So this is the cofunction identity. The sine of some angle is going to be equal to the cosine of his complement, okay? The sine of 1 degree is going to be equal to the cosine of 89 degrees, because 1 plus 89 is 90, okay? This works for any of the functions. Tangent of an angle is going to be equal to the cotangent of the complementary angle. Secant of the angle is going to be equal to the cosecant of the complementary angle. This is useful when you want to compute the sine or cosine of some angle based on some information that you may have already about its complement. Okay? Also, it helps show the symmetry in a lot of other situations. These are the basic identities, and most of the time, whether you're going to do it by usage or just straight up memorization, you have to know these identities. These are the identities that come up all the time. They're used in all sorts of applications, and they have to be used readily and quickly. So all 4 of these categories you really need to memorize these. Now, I say memorize, I've said before, I'm terrible at memorizing. What I do is you just use them over and over again, or think of them in a diagram or some kind of way, okay? But the more you build on these, the more they'll keep sticking to you. And some of them are more obvious than others, but you must know these identities. You have to know them to succeed very well in trigonometry. Let me finish up this little in-between lecture video here with using a couple of examples that put these identities to work, okay? So the cofunction identity is going to be useful for these, and then I'm going to use all of the other ones for this example. So rewrite these ratios in terms of a complementary angle. So I've got cosecant of 57 degrees. And it says a complementary angle. So what is the complement of 57 degrees? Remember, the complement of an angle is whenever you do 90 degrees minus that angle, okay? And what we're just talking about were the cofunction identities. So cosecant is the cofunction of secant. Remember, the co in these co-functions, cosine, cotangent, does not mean co as in co-worker or working with or being alongside. That's not what the co means in these, by the way. The co stands for complementary. So this is complementary secant. It is the complement of secant. Okay? So not only complementary angles, these are complementary functions. So if you switch a complementary angle, you are also switching a complementary function. So basically, you can call this the complement of that, right? So what I end up with is that the cosecant of 57 is equal to the secant of 90 degrees minus 57 degrees. So we're going to have 33 degrees, okay? In your calculator, you can check this, by the way. Remember, cosecant is 1 over the sine. So if I hit 1 divided by sine 57, like so, I get 1.192. And then over here, secant is 1 over the cosine. So if I do 1 over cosine of 33, notice I get the same thing, 1.1923, yeah. Okay? Not a coincidence. All right, let's do it again. The sine of 11 degrees. The sine of 11 degrees, sine is going to be complementary with cosine, and the complement of 11 is 90 degrees minus 11 degrees. Okay? I'm going to change this one, by the way. We'll make that one more interesting. So that means that I'm going to get the cosine of 79 degrees. Again, you can punch both of those up in your calculator, sine of 11 degrees, cosine of 79 degrees, and you'll see that you get the exact same value. Now right here, I decided to switch it up because I want to do one in radians here. Let's say the cotangent of pi over 5. Okay, now that's not one of your memorized angles. Pi over 5 is not one of the memorized ones, but it makes for a good radian angle. Notice there's no degree marker, right? Okay, so the complement of cotangent is tangent. And since this is in radians, I will not use 90 degrees. I will use pi over 2 minus pi over 5. Like so. So then I will just have to reconcile those two fractions. This will be equal to the tangent of, these going to be a common denominator of 10. right? Because times 5 and times 2. Times 5 and times 5 will give me 5 pi, and times 2 and times 2 here will give me 2 pi. So that's going to be 5 pi minus 2 pi. It's going to look like this. 5 pi over 10 minus 2 pi over 10. Okay? That's where I'm getting what I'm about to get here, which is 3 pi over 10. Okay? And again, if you're in doubt on that one, you can also check this in your calculator. Your calculator has the ability to do radians. You notice the little DRG button here. You may have already seen it before, or we may have talked about it before. If I hit that one, I can switch over to radians. And then you'll see the little RAD in the display there. Okay? So then to do cotangent, I just need to do 1 divided by tangent. So 1 divided by tangent. And then pi is one of my buttons, divided by 5. Okay? So that would be the cotangent of pi over 5. 1.376. And then now I'll also do the tangent of 3 times pi divided by 10. And you'll notice it's the same thing, 1.376. Okay? So those are the cofunction identities and the ability to switch complementary functions and angles. Here, this is what I was trying to allude to before. If I know one of the trig functions, just one of them, one trig ratio of an angle, then we can find all of the other ones. There's actually 2 different methods, okay? One of the methods is what I call the ACT method, because they teach you to use it on a test, is to just draw the triangle with the angle in it, and set up the ratio that you know, and fill out the sides. I'll show you that one real quick. If I just draw some triangle over here, right, and put theta as an angle in a right triangle, it says the secant of theta is equal to 5. Well, don't forget that's 5 over 1. And the secant of some angle is the hypotenuse divided by the adjacent, right? Secant is the reciprocal of cosine. So the hypotenuse must be 5 and the adjacent must be 1. From that information, I can use Pythagorean Theorem to fill out the third side. That would be 5 squared is equal to 1 squared plus a squared. So I have 25 minus 1. 24 is equal to a squared. Square root of 24 is equal to a. And of course you'd simplify that. Square root of 24 is 2 square root of 6. So I would put 2 square root of 6 over here. From this triangle, you can set up any of those trig ratios, any of them. Okay? So that's one way to solve this question. All right, we've basically already solved it because I can set up opposite over hypotenuse, adjacent over hypotenuse. You can get the sine, cosine, tangent immediately from that graph, okay? However, I'm going to also do this one the other way now. I know all of the information there and the answer is there, and yes, that was quick and easy. The method that we're about to employ here is not necessarily quick, and it's not necessarily easy. However, it is necessary. And I'll tell you why. I know in my classes, I would always tell them by using identities only, because I really want my students to learn these identities. They come up so often and they become so useful with simplifying things later, and you need to know them quick. So this is a perfect way to introduce and to get used to using those identities. All right, so here we go. I'm going to start with the fact that secant theta is equal to 5 over 1. Okay, so that's the first trig ratio of the 6. Immediately from the reciprocal identities, I know that cosine of theta is equal to 1 over 5. That's just knowing that secant and cosine are reciprocals. From here, I can go 2 different directions. But either way, I'm going to use a Pythagorean identity. There is the secant theta, which is tangent squared theta plus 1 is equal to secant squared theta, or the cosine theta Pythagorean identity, which is sine squared theta plus cosine squared theta equals 1. I'm going to go with that one. Okay, I'm going to go with the cosine one, just because it's more well known and it's the one that you'll probably be using more often. Okay, so from here, I'm going to say sine squared theta plus cosine squared theta equals 1, which is my identity. And then sine squared theta plus cosine theta is 1/5. And it's squared because that's the identity. Next, sine squared theta plus, this is going to be 1 over 25. And I'm going to write 1 over here as 25 over 25. And the reason for that is because I'm going to be solving and I need a common denominator. Okay, so I'm going to subtract the 1 over 25, like so. And notice sine squared theta is equal to 24 over 25. And I'm going to square root both sides. That's going to give me the square root of 24 over 25. Okay, now all you sticklers out there, you're going to say, hey, wait a minute. Every time you square root both sides, you're supposed to put plus and minus. You're right. We haven't discussed negatives with trig values yet, and we're inside of a right triangle, which never gives negative values. So I'm assuming the positive because of this statement here. Theta is in between 0 and 90 degrees. Okay, and then I can simplify that. So sine theta is 2 square root of 6 over 5. So now I have sine theta. And that's just using one Pythagorean identity. Okay, well, if I know sine theta, that means I also know cosecant theta, right? Cosecant theta is going to be the reciprocal. So that would be 5 over 2 square root of 6, which of course you may want to rationalize multiplying top and bottom by square root of 6, which would give me 5 square root of 6 over 12. Right? Square root of 6 times square root of 6 is 6 times 2 is 12. Okay, so now I just have 2 left, right? Well, remember, I've got the quotient identities too. Sine theta divided by cosine theta is equal to tangent. Okay, so let me separate this out here and this out here. Tangent theta is equal to sine theta divided by cosine theta. So that means that tangent theta, I'll go ahead and write it out. Let me write it out. That means that tangent theta is going to be equal to 2 square root of 6 over 5 divided by 1 over 5, right? Because that's sine divided by cosine. Okay, so that means that tangent theta is equal to 2 square root of 6 over 5 times 5 over 1. And of course the 5's can reduce, showing me that the tangent of theta is equal to 2 square root of 6. And now I've got tangent of theta, and there's only one left, the cotangent, which is the reciprocal of tangent. So then cotangent theta is equal to 1 over 2 square root of 6, which, like before, you're going to want to rationalize. So that would be just square root of 6 over 12. Okay? So take a look at all of the identities that I used, right? I used a reciprocal identity, one of the basic ones. In fact, I used those 3 different times, right? I did the reciprocal here, I did the reciprocal here. I used a Pythagorean identity, and that's the one you should always use whenever you have a single to get to another one that's very different, a different kind of single, okay? So I got from cosine to sine. I could also have gone from secant to tangent with a Pythagorean, and I could have gone this way, which would have allowed me to come back around the other two anyway. Okay? So I used all three of the basic identities there to go from one to the other. And that's just one application where those can be useful for that. Okay? So I hope all of this has helped you see the important angles and the very basic important identities. The identities make up all of the algebra that we do in trigonometry because it doesn't mix well with a lot of other things. So the identities are extremely important for you to know and to remember. Okay?